Hello again, pre-calculus students. In this video, we're going to learn how to find the zeros of polynomial functions, which, as we've learned earlier, is also going to tell us about how to find factors of polynomials. I want to start with the fundamental theorem of algebra. It says, if you have a polynomial of degree n, then that function has at least one zero in the set of complex numbers. But from that, there's a lemma. And a lemma is like, I guess the way to describe a lemma is like, it's another theorem that follows from this one, but it's so simple and so basic, we're not going to call it its own theorem. It's just like a sub-theorem of this one. And yet, it's this lemma that's actually the big deal. Because it says that if you have an nth degree polynomial, then that polynomial will have exactly n complex roots. Now, as I stated in my last video, saying they're complex does not mean they're imaginary, but it will have exactly n complex roots. And as we've learned previously, an nth degree polynomial can be factored as some constant a times x minus root number 1 times x minus root number 2, etc., all the way out to x minus its nth root. So if a polynomial that has 5 roots is going to be, some constant times x minus root 1 times x minus root 2 times x minus root 3 times x minus root 4 times x minus root 5. That's the only way you can get a 5th degree polynomial. It's the only way. Now, all of those roots are complex. They may be real roots, imaginary roots, or some functions will have both real and imaginary. If your polynomial has real coefficients, in other words, you're, something x cubed plus something x squared plus something x plus a constant, if there's no I in there anywhere, then any imaginary roots you have will always, always, always come in complex conjugate pairs. And of course, I'll show you more of that in detail in a few minutes. That means that if your polynomial has real coefficients and the imaginary roots always, always, always come in complex conjugate pairs, that means that if a plus bi is a root, then a minus bi must also be a root. So 2 plus 3i is a root of what polynomial with real coefficients? Now, I'm a math major. I was trained formally. Some people leave that with real coefficients part off. They just, well, the students know we're not doing 2i x squared and stuff. I would rather be explicit about it and be, factually accurate. And, to the point of being a little bit repetitive, but I want to point out that this only happens if your polynomial has real coefficients. So if 2 plus 3i is a root, and your polynomial has real coefficients, then 2 minus 3i must also be a root. And there are 2 ways we can find those roots, and we covered those in a previous class, but let's do it again anyway. Way number 1. As I said, any polynomial can be written in factored form, which is a constant a times x minus 1 root times x minus the other. Well, if you let a equal 1, because that makes things simple. Then if we, distribute the negative 1 here and the negative 1 here, we get x minus 2 minus 3i and x minus 2 plus 3i. Now you can see that's kind of like a minus b times a plus b, which is a squared minus b squared. And so we know that that's going to be, if our a is x minus 2 and our b is 3i, we can write it this way. Well, we have to FOIL this using this formula. 3i squared is -9, so minus a -9. There's the polynomial that has these two roots. And you can check that with the quadratic formula. Now, that's pretty cool. I like it, but I like this other way even more. It requires very little extra memorization, but it's a lot more elegant, as we say in math. And that is, I have taught you is that if you have a quadratic, and if you take your two answers that you get from the quadratic formula, negative b plus something all over 2a and negative b minus something all over 2a, and you add them together, you will always, always, always get negative b over a. So the sum of the two roots of a quadratic is negative b over a, and the product of the two roots of a quadratic is c over a. Okay, add these together, you get 4. Multiply these together, you get 13. So if you let a equal 1 in each of these, then negative b is 4, b is -4, c is 13. Boom, there is your quadratic that has these two roots. Like I said, elegant. This is brute force and ignorance. I like that too. But sometimes you want to see it pretty. This is how you do it pretty. You remember these two formulas. So there's only, what type of problem has only one real root, and what's the simplest type of graph that has one real root? A line. And that would turn out if that real root is 7, then you can go, remember factored form a times x minus the root. Well, if a is 1, x minus 7, boom, there's your root, there's your equation, you're done. Roots of +3 and +5, well, x minus 1 root, x minus the other, and you can get it. Or you could say, add them together and you get 8. Multiply them, you get 15. No, there's your -8 because it's negative b over a, and there's your c over a. Now here's where I get to be a little bit tricky. I say, what is the simplest polynomial with real coefficients that has 2i and 5i as roots? Well, if it's 2i and 5i, those aren't complex conjugates. But if it's got real coefficients, then imaginary roots will always, always, always come in complex conjugate pairs. So the number 0 plus 2i, its conjugate is 0 minus 2i. 0 plus 5i, its conjugate is 0 minus 5i. So if you do it the first way, where you just do x minus each of the roots, this is like a minus b times a plus b is a squared minus b squared. That's going to be x squared plus 4. This one's going to be x squared plus 25 when you FOIL it out. Now you FOIL these, there's your answer. Or negative b over a. You, for these two roots, the quadratic that gives you these two answers, well, the sum is 0, the product is +4. So that means a is 1, b is 0, c is 4. You get x squared plus 4. Same thing here. The sum is 0. The product is +25. So negative b over a must be, let's see, b must be 0, c is 25. Then multiply those two quadratics together to get the 4th degree polynomial that has these 4 roots. Now, on page 158 of our current text, we say find the polynomial that has these roots. Well, these two are real. So you know there's going to be an x squared minus 4 in there, because you know if 2 is a root, then x minus 2 is a factor. Negative 2 is a root, x plus 2 is a factor. These two multiplied by give x squared plus 4. Now, negative 7i, if it's a polynomial with real coefficients, then 0 plus 7i must also be a root, because with real coefficients, imaginary roots will always, always, always occur in complex conjugate pairs. So here they are. Well, you can tell by looking that this is going to give us x squared plus 49. There is our graph. Our equation. Now, how can it only have 2 reals and 2 imaginaries? Well, it could look like this. Could look something like this. If you ask about it in class, we can go to the Desmos and graph this and see what it does in fact look like. And you'll see that it crosses the x-axis only 2 times. And that's where the 2 real roots are. Yeah. This type of problem is fun. This is great algebra, by the way. I tell you that 5i is a root of this. What are its other roots? Well, you could factor it, and it turns out, oh, look at that. You can factor and get all 3 roots. That one was pretty easy to factor. Another way to do it is to say, well, if 5i is a root, then negative 5i must be a root. So factors must be x minus 5i and x minus negative 5i, which means x squared plus 25 goes into this polynomial. I do my polynomial long division, and I get a 0 remainder. So the answer up here is x minus 2. So 2 must be another root. So my answer is, if I'm told that 5i is a root of this, what are the other 2 roots? They are negative 5i and 2. I got that doing that 2 different ways. Here's a third way. I know that if 5i is a root, negative 5i is also a root. The sum of those is 0. The product is 25. So I know that x squared plus 0x plus 25 must be a factor of the whole polynomial. And that's where I get my x minus 2. There's a fourth way. You see how we're combining a lot of the things that we've learned over the last few lessons. If 5i is a root, then I know I can do 5i. Here's my, what's the entire polynomial? I've forgotten now. It's 1x cubed minus 2x squared plus 25x minus 50. I divide 5i into it, bring the 1 down. 1 times 5i is 5i, and I add. Multiply these by 5i, and I add. Multiply by 5i, and I get 0. So that proves that 5i is a root because I got 0, but what it tells me is it's x minus 5i times this polynomial, because that's got to be an x squared, that's an x to the first, and that's a constant. Notice that this polynomial does not have real coefficients, because we've already taken one of the imaginary ones out. Alrighty, so let's do this one. We know that 5i is a root, so we know that negative 5i must be a root of this. So there's our negative 5i. 1 times negative 5i, negative 2. Oh, look at that, comes out perfectly. So our last root is 2. So 4 different ways we were able to get those roots. All right, some books call this the rational root theorem, some call it the rational zero test. But anyway, here's a polynomial, a constant, and we're gonna go with real coefficients. I'm sure that this actually applies to all polynomials, but we are only going to do reals on this one. Some constant times x, maybe x to the fifth, plus another constant times x to the fourth, plus another constant times x to the third, dot, 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 all the way down to a constant times x plus a constant. Now, if x has rational roots, so rational roots doesn't mean just like numbers like 3 and 5. It means like, could be 3/4, where 4x minus 3 is a factor of your polynomial. Think of it, if 4x minus 3 is a factor, so 4x minus 3 times something equals 0 because your y value has to be 0 at the roots. 4x minus 3 equals 0, x is 3/4. A rational root. So if that's true, if you have rational roots of the, if f of x has rational roots, p over q, then p will be a factor of this number, and q will be a factor of this leading coefficient. Example problem is the checkpoint problem on page 158 of your text, of the current textbook that we're using. If there are any rational roots of this polynomial, it will be the numerator of that rational number will be a factor of 8, and the denominator will be a factor of 1. Well, here are all your factors of 8. Here are all your factors of 1. So since the plus or minus 1s, that's not going to affect anything. There are 8 numbers you have to check using your synthetic division. Am I that mean? Not always. Usually I'll give you a graph as well, and you'd look and you say, okay, there doesn't appear to be any root. The graph doesn't appear to be crossing the x-axis anywhere near this number, for example, either of these numbers. So I would only say, okay, the graph looks like it's crossing somewhere. I'll check that number using my synthetic division, because maybe it's not a rational number 2/3. Maybe it's the irrational number 0.6667, 6667, 66667, etc. using that pattern. That would be an irrational number. So what we would do is we would find the rational number and check. So what I would say here is if we graph it using the Desmos, we can check if any of these numbers appears close to where the graph is crossing the x-axis. Now, this is an x to the third problem. Any imaginary roots will occur in complex conjugate pairs. So at most, there could only be 2 imaginaries, which means there has to be at least 1 real here. How do we know that? From what we've learned before. Before, we have learned that x cubed with a positive leading coefficient look like that. And the, let's see, if this goes off to negative infinity and this goes off to positive infinity, the intermediate value theorem says that the function takes on every value between negative infinity and positive infinity. It means it must take on 0 somewhere. So that would be our root. Now, maybe it looks like this. That would be the case if it had 1 root. Oops. There we go, it's a little better. Here's where it would have 2 roots, here and here, but this would be a double root. And here's where if it looks like that on the x-axis, it would have all 3 roots. Up here would be again a double root and a real, and here would be another 1 real and 2 imaginaries. Depends on where the x-axis is on the graph. I've stayed really late after school to make this video for you. I'm gonna go home and spend a couple hours doing my own college class that I'm taking. So hopefully you got some good information out of there. We'll talk about it in class. Have a great day.